folks. Today we're going to talk about inductive reasoning and conjecture. Those are probably three very new words for you, maybe not reasoning, but inductive and conjecture are probably new. By now, if you've noticed, this section is not correct. An ISN page stands for Interactive Student Notebook page, and we don't have our interactive student notebooks this year. So we're going to go ahead and move into the actual meat of what we're doing today. The instructions say, just very simple at the beginning, find the next item in each pattern. Now, this one right here is not part of the pattern. The pattern is here. So the pattern is 3, 6, 9, 12, 15. So if you think about it for a moment, what would come after 15? Well, 18 would come after 15 because the pattern is that we're counting by threes. The next pattern is arrows. So we have an arrow pointing, kind of if we're talking about cardinal directions, it's pointing west and then northwest and then north and then northeast. And so after that would just be east. And finally, we have our third pattern, Sunday, Tuesday, Thursday, blank. Well, this pattern is giving us every other day. So we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and the next should be Saturday. So today is about recognizing patterns. Inductive reasoning is reasoning that is based on patterns that you observe. So now you kind of know what at least one of those words are. Inductive reasoning is based on patterns you observe. So I used inductive reasoning on number 1 to assume that the next term was 18, based on the pattern that I see of counting by threes. I used inductive reasoning on number 2 to determine that the next arrow would be to the right based on the pattern. And I also used inductive reasoning on number 3 to determine from the pattern that the next term is Saturday. A statement that you believe to be true based on patterns So a statement you believe to be true based on patterns is called a conjecture. So on number 1, the conjecture is 18, because that's a statement I believe to be true based on the patterns using my inductive reasoning. On number 2, my conjecture is the arrow to the right, and on number 3, my conjecture is Saturday. So I'm going to go ahead and scroll down to the examples. Example 1, and you're just going to make a kind of a guess here, kind of a hypothesis if we're thinking about in our science classes. The product of an even number and an odd number is blank. So I want you to insert something here as a guess. It doesn't matter if it's right or wrong, just guess something. The product of an even number and an odd number is blank. It does need to be believable though. Don't put hippopotamus because that's just not going to be true. So we're going to list some examples and look for a pattern. I'm talking about the product of an even number and an odd number. So here I've got 2, an even number, times 3, an odd number, and that gives me 6. Again, I have the product of an even and an odd number. 2 times 5 is 10. The product of an even and an odd number, 2 times 7 is 14. And the product of an even and an odd number, 2 times 9 is 18. So based on this set of products that we have, what pattern do you notice? I notice that the product, 6, 10, 14, 18, every time those numbers are what? Those numbers are even. Even, even, even. So the conjecture is that the product of an even number and an odd number is also even. And this conjecture we arrived at using inductive reasoning. So again, maybe you guessed that up here, maybe you didn't. It doesn't really matter. That's just your hypothesis. But the conjecture is what we observed. What we observed and what we thought after we observed. So part B says the following is Pascal's triangle. List the numbers that would occur on row 7. So this is row 1, row 2, row 3, 4, 5, 6, and then you're going to list the ones that occur on row 7. So pause your video and try and figure out what you think goes on row 7. So in class, we might have some discussion. We might have some people come up and talk about what they think row 7 looks like. I do notice, though, that we have 1s going down these diagonals on the outside of the triangle. So we're probably going to have a 1 there and a 1 there, right? I also notice that this second little, like, smaller inserted triangle starts at 2, and then 3, and then 4, and then 5, and so this is probably going to be 6, and same thing over here, 6. Okay, and the next one starts out with a 6, and then we go to 10 and 10, and so not really sure what's supposed to be here. Maybe you can look for another pattern rather than just looking at triangles, smaller triangles. I do notice that if I have 1 and 1, if I add them together, I get 2. And if I have 1 plus 2 and add them together, I get 3. Well, if I have 3 plus 3 and I add them together, I get 6. So I do notice that above each number, there are 2 other numbers, kind of, it's in the window between them. And if you add them, you should get the next number in the next row. So 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15 again. And 5 plus 1 is 6. 1 plus, there's nothing out here, is 1. So this is the 7th row of Pascal's triangle. So the conjecture, based on our inductive reasoning, the pattern that we have noticed, our conjecture is that the 7th row is 1, 6, 15, 20, 15, 6, 1. But that pattern is something that I want you to take a moment to try and describe. So I'm going to pause the video and I want you to do the same, and I want you to write under here kind of the pattern that you described. So hopefully, sorry about that. Hopefully you said something like each number is the sum of the 2 numbers above or in the previous row or something like that. So just make sure that you are able to describe how to get to the next row of Pascal's triangle. I'm going to go down a little bit more. Now, a conjecture is something that we believe to be true based on a pattern. To show that a conjecture is actually true, you must prove it, which is something that we do a lot in geometry. Slightly easier most of the time is to show that a conjecture is false. And the way you show a conjecture is false is that you only have to find one example in which the conjecture is not true. This case, this one example, is called a counterexample. The counterexample can be a drawing, it can be a statement, or it can also be a number. So in example 2, the conjecture is that for all positive numbers n, 1 over n is going to be less than or equal to n itself. So we're going to have some examples, and we're going to see if we can figure out either a counterexample or if we can prove this. So let's let n just be 1. That's a positive number, right? And the conjecture is that for all positive numbers n, this is true. So let's let n be 1, just a normal positive number. Since 1 over n is just 1, and 1 is equal to 1, well, then the conjecture is true. Because the conjecture said that 1 over n is less than or equal to n. So the conjecture is true here. I should say this situation is true. So let's try again. Let's try n equal to 2. That's another positive number. So since 1 over n is really 1/2, and 1/2 is less than 2, well then the conjecture here is also true. Because the conjecture was that 1 over n is less than or equal to n. If it's less than, well then that is true, that fits. So let's try another positive number. Let's not go to 3, let's actually think in a different direction. Let's go to 1/2. So since 1 over n is 1 over 1/2, which is really just 2, and 2 is greater than 1/2, the n value, well, here the conjecture is false. Here the conjecture is false. So we have found one example where the situation is false. What is that called? Well, that's called a counterexample. So there is a counterexample, yes, and that counterexample is when the positive number is 1/2. That makes the conjecture false. So we've proven that this is not true. So let's try another one. The conjecture is that the radius of every planet in the solar system is less than 50,000 kilometers. And in the table, what are you given? You're given the planet's what? I'm given the planet's diameter. Well, if I'm going to compare diameter and radius, I need to know the relationship between the two. Remember that in a circle or a sphere, the radius is half the distance of the diameter. So if I took this radius and I multiplied it by 2, I would get the diameter. So radius times 2 equals diameter. So if I take this and I multiply it by 2, well, then that's 100 kilometers, correct? The conjecture is that the radius of every planet in the solar system is less than 50,000 kilometers. So the diameter must be less than 100,000 kilometers. Is there a counterexample? Yes. In fact, there are 2 counterexamples, Jupiter and Saturn. Jupiter and Saturn both have diameters greater than 100,000 kilometers, so their radii must be greater than 50,000 kilometers. So this conjecture is not true. And finally, we have some examples for you to improve your reasoning skills. These patterns are different, and these patterns, most of them are difficult. You're asked to find the next term and explain the pattern in words. So I have all of the answers on my page, but I want you to pause the video and try to figure some out. Some of them take quite a bit of time, and some of them you're just not going to be able to get. If you Google these answers, you will find them, but that's cheating. So try to figure some of these out on your own. Pause the video, and when you're ready to check your work, you're welcome to unpause.